Okay, so describing what happens when a soluble ionic compound enters water, why does this happen? So what happens when a soluble ionic compound hits H2O?
The cation and the anion separate?
Why?
Because they're charged. They're polar.
Okay, so your answer to this needs to include something about water. Water is pulling the molecule apart, right? The fact that the polar water molecule why is it doing that? There we go. Okay, so and why does this happen? It happens because water is polar. So what would happen if you were to take an ionic compound? So give me an example of a common ionic compound.
Sodium phosphate.
That's not a compound. Sodium phosphate, I'm not really sure how common that is to you guys, but table salt. What happens when you take table salt and you throw table salt into olive oil? Nothing. Why? Because it's not polar. You cannot disassemble the ions unless the thing that's doing the disassembling has a positive and negative side, and oils don't have positive and negative sides. So if you want to flavor olive oil, throwing salt into it isn't really going to work for you, will it? Okay. So for these next, we want to balance the reaction. We want to add states where we can. We want to circle any ionic compounds. Okay, so do we have any ionics in the first one? No. No ionic compounds there. To balance it, looks like I need is it just a 12? And then an 11? All right, well that one was easy. How about states? Do the easy ones first. We can go with a liquid for the water molecule. What else we got?
How do you know it's liquid and not gas?
Does it look hot?
It has oxygen in it.
Where?
In the first.
No, it does not. It's got oxygen atoms in a molecule, but it doesn't have oxygen.
Oh, okay.
Huge difference, right? If it's got O2, yeah, you're talking combustion. But there isn't any O2 up there. It's oxygen locked up in some molecule. Anybody have any idea what that probably is?
Is it sugar of some type?
It's some sort of carbohydrate, for sure. You know it's a carbohydrate because the H's and O's match each other. Pardon me. The H's are double the O's. So I've got some kind of sugar there, and the sugar's breaking down into straight carbon, and the state for the carbon is what?
Solid.
It's just carbon, right? So you just look on the table and you see carbon's a solid. And then we already identified this other thing as a sugar, so what do you want to put down? Solid. Okay. Alrighty, how about the next one? What about it? Why would that be ionic? It's two nonmetals. Yeah, it's definitely not carbonate. Not yet. Balancing it? What do we need? So if I put a 2 in front of the CO2, then my carbons are balanced. And if I put a 3 here, my hydrogens are balanced. We good with that? And how many oxygens do I have on my product side? 7. product.
4 and 3, 7.
And then on my reactant side, 3. So if I make that a 6, then it's going to balance out. I'm sorry, 6 total. 3 total. 3, yeah. And states? For what? Why would you say that? Do you remember our 1, 2, 3 thing from Tuesday? Gas, or this isn't that thing that I talked about on Tuesday. I said 1 carbon, 2 carbons, 3 carbons was a gas, and then after that up to 12 was a liquid, and after that was solid-ish, and then we talked about asphalt. This isn't exactly the same thing though, is it? It's not a straight hydrocarbon, right? There's an oxygen in there, but it's still teeny tiny. So what do you think? All right, it's probably a liquid, but it's okay. It looks like, I don't know. It looks like ethanol to me, but I can't tell. So we'll go with a gas. Yeah, it's fine. Oxygen, gas. Carbon dioxide, gas. Water. You could say liquid, or you could say gas, because what kind of reaction is this? It's combustion, right? Oxygen on the reactant side, so it's a combustion reaction. Nobody's ionic there. Okay, how about this next one to balance it? What do you need to do? Not much. I think we need a 2 right there, and that's it, right? 2 in front of the ammonium chloride. Okay, so this one does give us one little example of making something a little easier on yourself. This is an ammonium ion, right? Is there an ammonium ion on this side? There is, right? So balance the ammonium ions instead of balancing the N's and the H's independently. So if it stayed from one side to the other, just go ahead and balance the ions. So we've also got this carbonate here, right? So there's a carbonate, there's one of those, and there's one over there. So that guy's already balanced. So you can save yourself a little bit of time if you recognize that a polyatomic ion stayed a polyatomic ion on each side and just balance the ions instead of balancing the atoms inside. Or you can balance the atoms inside, it doesn't really matter, it's just quicker the other way. States? Let's back up. Are these ionic compounds? All of them are, right? Metal, ion, metal, ion. So these are all ionic compounds. So then what are your options for ionic compounds? Aqueous or solid. So do you see any water? Don't see any water, do you? So what do you want to put? Solid. Okay, balance. I've got an aluminum, and the aluminum is balanced already, so that's easy. The sodium's already balanced. So let's go to the H's. I've got 4 H's on the left and 2 on the right. So if I put a 2 in front of the water molecule, everything's balanced except for the O's, and they might be balanced. So I've got 3 oxygens in my aluminum hydroxide, 1 in my sodium hydroxide, and then I've got 4 over there. So I'm good. All right, another easy one. So I've got aluminum hydroxide. What kind of compound is that? Ionic, so I get circled. Sodium hydroxide? Ionic. Sodium, something you have no idea what it is? Why? Because it's got what? Because there's a metal there, right? The sodium's there. I also have an aluminum in that as well. Not the water molecule. That's AlO2 is just one of the million polyatomic ions I didn't tell you needed to remember. So balancing did that. States. So this guy over here, I don't see any water on this side, so it's a solid. I don't see any water on this side, it's a solid. There's water on this side, so what am I going to do with this one? Why is this guy aqueous? Okay, so there's water and it's soluble because sodium's a group 1 metal, and it doesn't matter what the anion is. So yep, that guy's going to be aqueous. Do we follow that? There's water on the product side, so now I can decide if it's soluble, if it'll actually dissolve or not. And since there's sodium in the compound, the first rule for soluble ionic compounds is group 1 metals are soluble, period. So there's a group 1 metal there and some water, so it's going to dissolve. You good with that?
So if it, obviously, if it were not soluble, it would just be solid in water?
Yep. So if that would have been calcium aluminite, it would have been a solid. Because you don't have a rule for calcium, you don't have a rule for aluminite either, so it doesn't really matter. But you didn't have a rule for it, and you know it's ionic, so just, it's solid. And that's basically the, ionic compounds are more likely to be solids than they're not soluble than they are to be soluble. So if you don't really know, just write a solid and you'll probably be safer.
And the side that water is on dictates
Right.
that size.
Yeah, these are independent things. These are things, and then the reaction happens, and now I've got these things over here. So it's a, basically, the way you should think about this is, I have a test tube of stuff, I have a test tube of stuff, and then I mix them together. So does the fact that they make water have any bearing on the test tubes before? Yeah, it doesn't matter. Okay, so next one. I should have had you name all of these. That would have been better. So balancing this, I've got 3 irons on the right, so let's put a 3 in front of the Fe here. My sodiums, I have 3 on the left, so let's put 3 on the right. And I've got, well, let's use that little rule thing about the phosphates. Remember that? So I've got 2 phosphates on the right and 1 on the left. So I'm going to go ahead and put a 2 here to balance out my phosphates, which means I'm going to need to erase this 3. So my irons are still balanced. My phosphates are balanced. I can balance my sodiums if I put a 6 here. And that balanced out my chlorines for me, didn't it? Gave me 6 chlorines on the right, which went along with my 6 chlorines on the left. So the ionic compounds, everybody circle there. And then we've got I don't see any water, so it's a solid, solid, solid. Do we have names for these things? What's the first one?
Sodium chloride.
Iron 2 chloride. The next one?
Sodium phosphate.
Sodium phosphate. The next one? Iron 2 phosphate. And the last one? Salt, table salt. I actually can't remember if I really said this before. I think I did, but maybe not enough. So NaCl is salt. Are there any other salts up there? Anything that's an ionic compound is a salt. So salt is just a generic term for ionic compound. It's just we use salt to describe the one salt that we know a lot of. So the most common salt you come in contact with is the NaCl salt. So it just got named salt. But in reality, salt means ionic compound.
Every ionic compound
Is a salt. Yep. So a seashell or chalk, it's a salt.
Last class, I feel like there was some times when you said water wasn't present in the equation, but we could assume that whatever was happening in water.
Yeah.
Would that be like, would we be given that information like a word problem, say?
I said that in the heading for the topic that we were talking about
Yeah.
was reactions in water.
Okay, gotcha.
It'll be like that. It'll
Okay.
be blanketly obvious.
Gotcha.
So I've got sodium nitrate and sodium nitrite and oxygen, and I'm going to need some more oxygen. So if I put a 2 here, then I have some more oxygen. That gives me 6 oxygens on the left. And if I put a 2 here, that gives me 6 oxygens on the right. That's going to be problematic because I'm going to need to put a 2 here, right? If I put a 2 there, then I'm going to need to do what? Oh, that's it, right? That's better. Good. Okay. Ionic compound. Ionic compound. I don't see any water here. Solid. Solid. sodium nitrate, sodium nitrite, and then oxygen as a gas.
You're gonna have 4 oxygens. Oh. I'm just thinking 2 on the left, 2 sodiums, and I guess 6 oxygens on the left.
Yep.
And then 4 2. Okay, sorry.
4 plus the 2, right? Okay. Alrighty, so balancing, looks like I need 2 irons on the right-hand side. Okay. Looks like I need 2 potassiums on the left-hand side. Let's start over. There's a sulfate here, right? So there's 3 sulfates here, so let's put 3 sulfates over here. Okay. I can leave that 2 in front of the iron. So now I've got 6 potassiums. So to get 6 potassiums, I'll put 6 potassium hydroxides. And that's it, right? Because now I have 6 potassium or 6 hydroxides here, and I've got 6 OH groups here as well. They're all ionic compounds. Don't see any water. So we'll go solid with all these guys. Okay, next one, 7 carbons. So let's make 7 CO2s and 6 H's. So let's put 3 water molecules there. It's gonna be a problem, isn't it? It's gonna be a problem because I'm gonna have to double. So if I go with 14 here because I put a 2 here, then I can put a 6 here, and then I can get an even number of oxygens. And so over here I've got 28, so 34. There are 34 oxygens on the right. And so I need 34 over here. I've already got 4 in this first molecule. So then if I put a 15 in front of the O2, then I have 30. The easy ones we can put down, it doesn't really matter, a liquid or a gas for the water molecule, a gas for the carbon dioxide, a gas for the oxygen. 7. What do you think? It's a liquid or a solid because of the oxygens. We can put down a liquid. That's fine. Not a gas, though. We okay with that? Too big to be a gas? Okay.
So the hydrocarbon rule, like, loosely?
It's loose, yeah.
Okay, but if it's a true hydrocarbon, then it's like,
1, 2, 3, gas. 4, 12, liquid. After that, solidish.
okay.
Sulfuric acid, hydroiodic acid. Okay, so let's see. The sulfate disappeared on the right-hand side, so we can't balance using that rule. Let's go. There's a sulfur on each side, so those guys are balanced. How about the H's? If I put a 2 here, my H's are balanced now, right? 1, 2, 3, 4, 1, 2, 3, 4. And my oxygens, that's gonna be a problem. I'm gonna need 4 here for my oxygens. So now I've got 8, 9, 10. That's easy. I can put a 10 in front of this hydroiodic acid, right? And then I can put a 5 in front of the iodide.
No.
No? What's wrong with that?
You have the 2 H's over here also.
Is it 10? So I go 8 here,
Yeah.
and then go 4 here. That looks good. Then ionic compounds, nothing. States. So the first one's an acid, right? So what do you think? Okay. Liquid? No. No liquid, not a possibility. It's either a gas or it's aqueous. It's almost always going to be aqueous if it's an acid, almost always. So we'll go ahead and write aqueous. And then aqueous. It will not, it just won't form under room temperature conditions. The freezing point for it is well below normal situation.
The
all the acids that you see, there's a number associated with it, and that number is telling you its concentration. And the absolute most concentrated you can get hydrochloric acid is 37%, which is called 12.1 molar. So 37. If I get the most concentrated form of hydrochloric acid in the back, it's 37% HCl, and the rest of it's water. What happens if I try to make it 38%? It just turns into a gas and leaves. It will actually not stay in the water. And for us to use hydrochloric acid, you either use it as a gas, which is kind of a pain in the butt when I'm trying to dump stuff into a beaker, or I make it aqueous, because you can make it a liquid at this temperature. So aqueous. What about this H2S? You could say aqueous, but does anybody know what that stuff is?
Sulfuric acid.
Is it There's no O. Hydro, right? There's no O. Hydrosulfuric acid, but most people just call it dihydrogen sulfide. Does that name sound familiar? From what?
Covalent nomenclature.
I mean, in everyday life. Rotten eggs. Rotten eggs. So now what state is it? Gas. Oh, you're smelling it, right? So it's in your nose. So this guy's a gas. If you put down aqueous, that's fine, because what's on that side of the we've got some water here, right? As a liquid. And then iodide is a solid. It's a super weak solid, but it's a solid nonetheless. Questions?
The way iodide, isn't that what they use like pre-surgery? Like,
It's
like iodine.
So you said iodide, correct?
Iodine.
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 Okay, so iodine is a solid at room temperature, but you can get it into a liquidy kind of state. What do you think iodine would do if you put it on your skin? Yeah, it would evaporate, but it'd be easier to wash it off. What column is it in? It's in the column of elements that do what? Steal electrons, okay, but more everyday lifey.
Kill bacteria.
Kill stuff, right? Everything in that column in its elemental form kills bacteria. So does it make sense that they put iodine on their skin? Why are they using iodine and not fluorine? Because they want to have hands. They like hands. Because if you put fluorine on you, it would seep through your skin and it would just chew away your bones, and there'd be nothing there. There'd just be like skin and muscle and no bone. So that'd be a bad idea. So how come they're not washing with chlorine water? They used to, but it's bad for your skin. Bromine, some places still do. Bromine water, it's this like, I don't know, it's sort of like a mix between this orange and this brown kind of color. When it's thin, it looks more orangey. When it's thicker, it looks more brown. And then you can use the purpley, browny colored iodide. So they use the bromine and the iodide because they're less, I mean, if you're going into surgery twice a day, every day while you're at work, and you have to scrub in for 20 minutes before you go in, what's that going to do to your hands, your forearms? Not going to be much left of the skin, right? So you want to use something that will make sure everything's dead, but you don't want to destroy your epidermis. So it's the least corrosive thing that will kill everything. It's the least worst thing. How about that?